Before we move on, we need to do an intro to vectors. I'm not going to get really deep into it. That's what linear algebra is for. But we need a little bit to do the next section. So what exactly is a vector? A vector is an entity with a direction and a magnitude. We can draw it. It might look like this, or it might look like this, possibly this, or that, or another thing, or that, or this, or that. You draw an arrow with a length and going a certain direction, that's a vector. These are all vectors that are just floating around in space. We want to find a way of describing these vectors. We will typically describe a vector with something like a v or u or w with a line over it. V is the vector that goes x over and y up, so we will denote it angle bracket xy. The angle between a horizontal and the vector is known as its direction. We also care about the length of this vector. To find the length, we just use the Pythagorean theorem. We have the square root of x squared plus y squared. This length will also sometimes be called r because of polar coordinates, which we don't care about that right now. Another way of denoting the magnitude is saying the absolute value of v. I say absolute value because if you think about it, absolute value is the length of your number. If you say the absolute value of -3, you get 3 because it's 3 units from the origin. The magnitude is just another way of measuring length or magnitude size. Now theta, how can I get at theta? Well, if I know x and y, the tan of theta has to be y over x. So if I take the arctan of y over x, I'll get my theta. A couple more things I want you to know is we can write x as r cosine theta and y as r sine theta. Sometimes that might come in handy. So what can we do with our vectors? Well, we can add them. Suppose we have two vectors. Boom. A is 1, 3 and B is 2, 2. To add vectors, you add them component-wise. The first components together, the second components together. So A plus B will be 3, 5. And if I want to draw a picture of what's happening, you've got A goes 1 over and 3 up, and then at the end of A, you can attach the B vector and you go 2 over and 2 up. So the sum is represented by that green arrow, which goes 3 over and 5 up. Nice thing about addition of vectors is it's commutative. I could say B plus A and I'll get in the same spot. What else can I do? Well, I can multiply vectors by a scalar. A scalar just means a number, not another vector. Suppose A is 1, 3. If I multiply it by 3, that effectively stretches my vector. It's now 3, 9. I can multiply it by -1. This flips it so that the vector is going in the opposite direction. In fact, the way we define subtraction of vectors is using this multiplication by -1. A minus B is the same thing as A plus -1 times B. The next slide is for those physicists in the audience. We have what's called a standard basis. And for physicists and some mathematicians who are more applied than I am, we have the standard basis for 3 space. I, j, and k. I is 1, 0, 0, j is 0, 1, 0, and k is 0, 0, 1. This just represents the x, y, z axes. In 2 space, we just use I and j, 1, 0, 0, 1. Now, as a mathematician, we would call I E1, and j would be E2, and k would be E3. And the advantage is I can go to 4 space and say E4, and E5, and E6, and E7, etc. We just add the appropriate number slots in our standard basis. One thing the standard basis is good for is writing a vector in terms of I, j, k, so you have numbers and vectors that you know how to play with. For example, if I've got v, the vector v equal to 2, -3, 5, I can write that as 2i minus 3j plus 5k. So we have standard basis. We know how to find the length of a basis. Sometimes, though, we want the length of we can find the length of a vector, but sometimes we want our vector to be of length 1. I just want to keep the direction, but I still want the vector to be of length 1. How do we do this? So these are called unit vectors. So suppose I have the vector 2, -3, 5, and I want to find a unit vector in the same direction as v. Well, this is pretty straightforward. We find the length of v and divide v by its length. Oh, I used the double lines here. Forget I did that. So I called u the unit vector because I take v and I divide it by its magnitude. Well, what is the magnitude of v? Well, you've got 2 squared plus 3 squared plus 5 squared square rooted. That gives me the square root of 38. So dividing each of those terms by the square root of 38, I get this beautiful vector. 2 over the square root of 38, -3 over the square root of 38, and 5 over the square root of 38. Now I know what you're asking yourself. Can you multiply vectors? Well, kind of, sort of, not really. Doesn't mean much to multiply a vector. But what we can do is something called a dot product. Suppose I have two vectors. V is v1 through vn, and w is w1 through wn. So that just means we're in Rn. I'm coming up with this is a very generic definition. So v dot w is just multiplying the corresponding components and then adding them all together. And what does this mean geometrically? Not much. Though it is nice in an equation, we know that v dot w is equal to the magnitude of v times the magnitude of w times cosine theta. And wow, isn't that a great thing to know, I guess? Let's look at this. Suppose v is 2, 4, negative 2, and w is 3, negative 1, 5. If I find the dot product of this, I get a negative 8. Super duper. What does that mean? Nothing to me right now. But let's remind ourselves, we have this formula over here. V dot w is equal to the length of v times the length of w times cosine theta. Let me solve for theta. So I have this expression. So I can find out that theta, or the cosine of that theta, by using the dot product and multiplying their magnitudes. Let's find their magnitudes. The magnitude of v is 2 square root of 6, and the magnitude of w is square root of 35. So that means cosine of theta can be written as negative 8 over all that shit. Let's simplify that. Well, make a decimal of it. And I get negative 0.276026. Yippee, that doesn't mean much to me right now, but I can do arc cosine of both sides and get that theta is equal to 1.85. This is in radians. And for those of you who still prefer degrees, it's 106 degrees. So I know that the two vectors are obtuse, meaning the angle between them is more than 90. Well, is that helpful? Does that help me do anything? Let's try a different example. Suppose I have 1, negative 3, 7, and 2, 3, 1. I'm going to find the dot product of these. I simplify and I get 0. 0 is magical. What does it mean? Well, if the dot product is 0, that means the cosine of theta is 0. Well, if the cosine of theta is 0, that means theta is pi over 2, which is 90 degrees. That means the two vectors are orthogonal or perpendicular. And that's a pretty nice thing to be able to check to see if two vectors are orthogonal. So this video had a lot of kibbles in it, kibbles and bits, trying to get scraping together all the things you need from vectors, but not giving you too much. Hopefully it wasn't too jointed and you could follow everything. The thing I want you to remember is the dot product, because we have to do that. Being able to add vectors, that's a good thing. Being able to find the angle between two vectors, that's interesting. Not sure we're going to use that as much, but we'll definitely be using the dot product.